Nice to meet you. Nice to meet you.
Yeah, thank you for having us to your channel.
Yeah, it's great. So I was at their channel on Tuesday, and we had a lot of fun talking about the M1. So this time they're going to talk about their DIY OS written in Rust. But first, why don't you introduce yourselves a little bit?
Okay.
Sure. So we are VTuber from our channel Low Layer Girls. So we talked about one of things like mainly system level programming in Japanese. And thank you for subscribing on our channel. So now we have
we have 6,000 subscribers. That's amazing.
Thank you so much.
Yeah, I am amazed that so many people were so many people were interested in our topic, like low level system level things.
Cool. I didn't even know there were VTubers doing this kind of stuff. It's so great.
Thank you. I think you are doing the same, right?
Yeah,
your stream is very
pretty
cool.
low level, right? Yeah.
pretty low level.
Yeah.
Yeah, we talked about operating system, programming language, like a browser. I'm making.
And sometimes prologue.
Yes,
it's not a low level,
yes.
but
That's amazing.
So this is our channel, so please subscribe if you want. And we are doing those stream in mainly Japanese, but we can understand English. So please feel free to comment, put a comment in English, and let's enjoy. Low layers.
Yeah.
Share the low layer love.
Yes.
Yeah, we love system level programming.
Absolutely. Then let me introduce myself and Asami-san each. And so I'm Hikalium, and I'm working on open source operating system, maybe you know, and my hobby is also writing a toy OS. So I'm touching operating system all the day, every day. 24/7, I mean, literally. And also I like diving into the virtual world like this. As you can see, maybe it is, the picture is hidden by us, but I wrote OSGsaku. OSGsaku is a homebrew operating system in Japanese. So I wrote this during the New Year holidays. And also, I sometimes write songs, and you can see my YouTube channel. The song is not. I'm not good at singing yet, so please don't expect too much. But if you are curious, please check. That's it. Okay.
Great.
So Asami-san.
Yeah, I know. Wait, I know you started to like operating system when you are. Like
elementary school student,
right? Yeah, it's so great.
Yeah,
that's amazing.
I found a nice book about writing an operating system, and since then I'm working on my toy operating system. So I already have over 10 years of experience in operating system. Thank you.
Amazing.
Okay, then Asami-san, please introduce yourself.
Yeah, let me introduce myself. I'm Asami, and I work on writing an open source browser. Maybe you have used it before.
Definitely, I'm using.
So my hobby is programming and fashion, arts and design, and reading books. Because you can see, I wrote a RISC-V emulator during my free time, and you can see the code in my GitHub. Also, I like fashions and writing, drawing. So the write pictures are my artifacts.
I think the picture is. Oh, okay. I was overlapped with the picture.
Oh yeah, sorry.
No problem. Which way should I go? Anyway,
Wait.
We can do this. We can do it like this a little bit better, maybe. No, it's about the same. It doesn't change a lot. Sorry. He's
Okay.
looking on top.
No problem, no problem. Oh. But Asami-san started programming quite recently, right?
Oh, yes. Originally, I was like a web front-end engineer. I started to write code, HTML, CSS, and JavaScript when I was like 18 or 19. When I was a university student, and I had been writing HTML, CSS, and JavaScript for 2 years. And after that, I was working on like a web backend engineer. As a web backend engineer, so I wrote like a Python, Go.
So you're working on
PHP.
server side.
Yes, right. Yeah, I was making like a web application and bots, the web APIs, and something like that. And after that, I started to be interested in like a low-level programming, like an operating system and the emulator and the programming language, etc. So I started to learn them by myself, and and now, yeah, I made a RISC-V emulator and a browser from scratch and something like that.
So
Yeah,
you
I
fell
hope-
into the whole of low level, right?
right.
The whole stack from top to bottom, right? From
Yeah.
web to writing emulators. That's so awesome.
From top to like a very bottom.
Yeah.
Thank you. So that's us.
Yeah,
And
today we gonna talk about our project. Like
Yes.
we call it like a Wasabi project, and this is like a
Oh,
hikalium.
actually, this is not a Wasabi project. It's a
Oh, okay,
liumOS.
sorry. Yeah, it's kind of different project, but similar one.
Yes.
So hikalium is making a toy OS, and
Yes.
I making a web browser that
Own it.
works on
Own it.
like that works on like a
It's like just an
How
OS in a web
OS.
browser. It's just a little experiment. It's so cool. Come on.
Of course, the functionality is limited.
yeah
and
very limited.
Yes.
This is a very early stage, so
it's a fake web
a
browser
fake
and a fake
web
operating
browser.
system, but it works. It works.
sorry, it just only like a parsing HTML, CSS, and JavaScript, so it doesn't have a much functionality. So, but we will add more functionalities.
That's amazing.
So this picture showing Kagami-mochi. Kagami-mochi is is a traditional Japanese New Year decoration, and Asami-san implemented. Asami-san wrote a CSS to display Kagami-mochi on the browser on my toy operating system. So that's cool, isn't it?
Yeah. Now my application browser application can like a pass like a div HTML div element and the CSS and the color background color and can how to say the positioning to the center. I don't know how
So
to say.
layout.
Yes, yeah, part of layout. Yeah, my application supports them.
Cool. So like the position, relative, absolute, that kind of stuff.
Not that so much, but yeah, part of them.
Part of
Part of it.
I think we need absolute attribute for writing Kagami-mochi using CSS. How it is written.
Yeah, right.
Anyway, we will go through the how it works from top to bottom today, so
Yes.
we can check.
It's gonna be
the
great.
code.
I'm so looking forward to this.
Thank you, and yeah, thanks for coming, everyone. This is very hacky stream, but
Yeah, I hope you enjoy.
yeah. So, is it okay
what?
to start checking the source code, or
I think so. Yeah. We can just jump right into it.
okay, let's go. And okay, so first I want to show you how our operating system works, and just type make run, and it will launch QEMU. And yes, it boosts my operating system, liumOS, and actually it has a GUI.
Window manager.
Yes, window management. Only limited functionalities are supported, but now and also I can type the characters, and I can see you can see the logo of liumOS like this. But this logo is written into frame buffer directly for debugging purpose, so this will be removed. Wakaru. And also you can type ls command, but those commands are implemented in operating system, so it is not implemented in user land. But as you can see, some files are loaded. It is not sorted because they are read from UEFI firmware directory. So, but you can see those files anyway. And also, here's our browser, browser rs.bin.
Yes,
so we will.
That's the application I'm writing.
Yes, and but before doing that, we can check IP command to assign the IP address. So I think you can send a ping. Is there a ping bin? I think. Okay. Ping bin is there. So ping bin, like 8.8.8.8 or something, and. Yes, app reply has been received. So now we can send app not only app but also ICMP packets.
So you have file system, networking, window management, and UEFI. It's a full OS.
Yes, but everything is ad hoc implementation. So they are not. The implementation is not sophisticated, but it works. It just works. And so I want to. So what was the command to launch Kagamimochi browser?
Yeah, browser rs.bin and default page. Hyphen default. Yeah, we can see the default page. Oh, no need to.
Only default?
Yeah, only default.
Okay.
Then we will see the default page, and the default page is currently like a Kagamimochi. And it's written, it's written in HTML and the CSS. So my application can like parse HTML CSS like this.
I can see like the debug prints with the like your parsing.
Sorry. It's messy, sorry.
Yeah.
And also
that's the most fun part because you can see how it works.
And moving window is very heavy because we only support CPU, not GPUs. So
it's like Asahi Linux, right? Now.
Asahi Linux only supports CPU now. All the window management things are done in CPU?
Yeah.
Whoa.
So this is the UEFI frame buffer?
Yes.
It's the same for Asahi Linux. We use the bootloader frame buffer.
We are doing the same thing.
Yes. So if it works for Asahi Linux, it's good enough, right?
Yes. Maybe. And so that's it. That's how. That is the example of how we can interact with our operating system. So let's start tracking with the source codes. And where to start, Asami-san?
Yeah, maybe we can start like an app browser RS and
browser RS. So as you can tell, browser RS is implemented in Rust. Actually, the operating system is implemented in C++, but we are writing a new operating system in Rust. So I will introduce it later. But this version is written in C++. But anyway, let's check.
Yeah, application is written in Rust. So my application too is too.
Mm-hmm.
The main script.
And so main function is here.
Maybe the interesting point is more below. Down. Or maybe lender is a main function, like a
Here.
Yeah, right. And
also here's a default flag parsing.
Right. It's a command parsing.
So if default is specified, then we will render the default page.
Yes.
Wait, the default
currently
page.
like
source default tree.
Oh, right. Page it's currently embedded. So that's the Kagami Mochi's page.
I see.
So we have a style tag and
so we can our browser can understand those CSS.
Right. Yeah.
Let's change the color of the background color. Which color
maybe
is
I can.
Let's check.
Let's check what kind of color I support.
Where's the renderer and HTML CSS? Okay, CSS.
I forgot the
moderate maybe.
Home.
No. Okay.
CSS home.
CSS.
I'm sorry, I forget the detail because I wrote this a few months ago.
No problem.
It's the same for me. Like, I've been on streams before where I was like, oh, this isn't done yet. And then I'm looking like, wait, I did do this 2 months ago. And then I
maybe layer.
Orange.
Maybe different file. So
Okay.
render layout, render tree.
Render tree. Orange.
Yeah.
Okay. So it is
Very
hard coded. Hard coded.
But we can.
I think at least.
Okay. Then
pink.
let's use pink. And what was the file? What was source? Default page RS. And
Right.
let's change the
ID2.
I did too, right?
ID2. Okay, this one.
Yes, right.
And color will be pink.
Pink.
And let's run again. Okay. So browser RS Bing default. No!
Yeah.
Now we have pink Kagami Mochi. I think this is not orange. Now this is peach, I guess.
Peach, right.
It looks like peach.
You can call it pink.
So yes, it's working.
Yeah, it works. Yeah, my application understands CSS correctly.
So how the CSS is parsed? Maybe we need to check render function.
Yeah, basically I don't know how to say maybe we can start HTML first.
Okay, HTML.
HTML token.
Token.
Yes, that's the start point. And if string comes to this file, so we divide string into a token, the HTML token, and the HTML token is.
Maybe the function name is tokenize or something.
I think so. Yeah, tokenize. I forget the exact name.
Let's track from top to bottom. Where is the render function?
And renderer, source renderer mode, I think.
Here it is.
Renderer.
So
And
HTML. So first we will pass the tokenize the HTML text and make a DOM tree, and after that we will apply style onto that tree. Oh, and is it supporting JavaScript?
Yeah, part of.
Oh.
But currently we don't. There's no way to make sure the JavaScript works correctly or not.
So we cannot change the DOM, I think, from the DOM.
Right,
From
and we
Clone, right?
we don't have a way to interact with our browser. So like for example, like an event. We don't have events in the browser, so like we cannot type any like a string in browser. So
we even don't have a function to print text on the
console
browser
log.
screen.
no console log, sure. So we support it.
I do later. So let's check the HTML tokenizer. Then HTML, where is the tokenizer? Maybe we can use tag jump or something. I'm not sure how to use. But okay, let's do manually. I'm not good at using Rust analyzer on Beam, but so
I'm not sure too. And there are HTML and the token.
Okay.
Yeah, that's
token.
you can see HTML tokenizer.
So new.
Yes,
okay.
right.
I see. So it's just initializes the state and those consume next input and those.
Yeah, that's the HTML tokenizer is implements iterator, and we need to pass HTML tokenizer to like a next parser, and we will use it in DOM, right? Yeah, and DOM.
It's a node and
parser. Where is the parser?
Oh,
No?
not this file.
P is upper.
I see. Parse. It's
Right,
parser.
exactly.
I found it.
Yeah, and there's a tokenizer in its in its member. And
yes.
Parser read next token in its during parsing.
I see. T is the HTML token.
Right, exactly.
I see.
And yes, tokenizer in charge of like making a token, and parser parser is responsible for making a DOM tree. And after making a DOM tree, we move to like a CSS tokenizer.
Tree.
Oh, right. It is like a function to make a DOM tree. And in like a HTML
spec
parsing, we have a like a HTML spec, and these like a step are well defined in like a HTML spec. Like all steps are well defined in HTML spec, and
the HTML5, right? There's like the super like descriptive.
Right,
like this.
Yeah. I remember that because like different browsers used to parse things differently when it was HTML4, and it was such a mess. And then when HTML5 was defined, they basically said, okay, we're just gonna write a parser in English.
right. Exactly.
Right, yeah.
So standardization is very important.
Yes.
You know.
To avoid tag soup.
Anyway, so if you are curious, please check the spec. This is our Bible, anyway. So
someone asked in the comments who wrote this code. So Asami-san wrote the browser, right?
Yes, Asami-san developed the web browser side, and I developed operating system side. And also, I forgot to mention that everything is made from scratch.
Oh yes. We mean we don't use like a standard library in Rust, and we don't use standard library.
It's core only, right? Like no STD.
Yes, core only.
Because no standard.
We have that a little bit of Rust in the Asahi Linux bootloader actually, and it's the same thing.
Really?
Yeah.
I should check it later.
It's because we want to do secure boot eventually, and we didn't want to have exploits in that part of the code. So just the part that loads from the file system, the next stage, and we'll check the signature, but it's not checking it yet. That part is written in Rust, and so we had to do the whole no STD thing and like hooking into the allocator and all that. So this is all the same thing, right? Like all the user space apps written in Rust are no STD, and then I guess you have your own like system call library or something like that.
So you mean where the system calls are implemented?
Yeah, like you must have your own like
Yes,
library,
yes.
right? Yeah.
Yes. Here's a library called liumlib, and liumlib provides all the system call implementation in assembly.
Luna says once they implement OpenGL, I can port Inotsutsudi to liumOS.
Ah,
And then we can do
Wow,
VTubing
great.
from liumOS.
which system calls are needed for OpenGL calls? That's
You need
difficult.
3D. What's the license for liumOS and the browser?
We are releasing our open system and source code in MIT license, so you can use them freely without any restriction, almost any restrictions.
All the Asahi Linux stuff is also, almost everything is like MIT or PSD, so if you want to take the GPU driver and port liumOS to M1, you can do that.
Oh,
Nice. Nice
thank you,
project.
thank you. I will, definitely check and reuse your work. Of course, I add you in our credit. So, and
Nice.
so
Yeah, we talked about like HTML
passing.
stuff.
Yes, and
And for example, let's see like how to pass div tag.
okay.
Maybe we can see
So
like
if div tag is inputted, what will happen?
so like HTML spec define multiple modes, kind of like it kind of like how to say
State machine.
yeah right, exactly. I forget. So state machine. So we can see like wait, what's the name? I forget the name. Mode maybe. Oh yes, insertion mode. That's defined in HTML spec.
This one.
So
this
yes,
Lina.
that's like a state.
Ah, I see.
So
Because
past-
some tags are some elements are not allowed to appear in somewhere. Like
yeah, correct. Yeah, we can write div tag only in body, not like a before body tag and like a not between like a head tag or something
I
like
see,
that.
I see.
So we need to define. We need to have state, some kind of state, and this is defined in like a HTML spec. So first we will start with initial mode, and if we see the HTML tag, we switch to like before we switch to like another mode, and also if we see like a body tag, we will switch to like an in body. In
Here
body,
it is.
yeah, in body mode.
You can see, if we read body and we will switch to insertion
Yeah,
mode
so-
in body. I see.
Yeah, we decide our behavior depending on current mode and next token. This can like decide our next behavior. So in div case, for example, like div can be like passed if mode is in body and next token is if. Yeah, that's exactly the point.
I see.
Yes. So
Oh,
if div is if we see div element, we add div element node to tree.
So end tag also has the same element kind, right? Pop until means.
Oh yes. Oh, that's a closing part.
I see.
Maybe we can see like a inserting part. Where is the? Can you find div again? Can you search div?
Here?
Where?
Oh,
Not the one.
Wait, div.
We have a comment
Where's,
saying, can you explain a little bit more about the different modes? Like the different modes you had earlier?
Oh yeah,
Size
yeah,
style
sure.
And all that.
The modes?
Yeah, insertion mode, right?
Insertion mode.
Someone asked about that.
Oh,
Yeah, insertion mode is it's hard to describe. Yeah, it's
maybe it's a good idea to check the spec.
right. Yeah, that's the insertion mode.
Yeah, it is. The insertion mode. Oh,
Many modes are defined in the specs.
is there any good figures that shows the insertion mode?
I don't
state
think
machine?
so. I don't think we have a good figure. Not sure. Oh, maybe someone make it.
I think so. Or maybe not. Please.
That's something else, I think.
Wait. It looks like it is not the one. Okay. Let's go back to here.
Oh, can you search like how browser works?
That's the good article.
Yeah, that's a very good article about to describe how browser works. And not the one.
Oh, not this one. Which one?
Where is yes, that's one.
This one.
Oh, it's
I
still
see.
Firefox.
And we can see the
HTML
diagram. Yes. Where is the drawing? Not the one. Oh, that's a tokenizations state machine.
I see.
Oh, that one.
This one?
Yeah, that's the insertion mode.
Oh, okay.
So that's a state machine for like a parsing HTML. So back dot is not important. Yeah.
So it's really just linear, right? It's not like for the body or the complicated tag nesting. It's really about the whole document, like progressing from HTML to head to body to the end of the HTML, right?
Yeah, it's almost linear, but like in there is an exception in like in body state.
Yeah, HTML spec has so many exceptions, right?
Yeah, but basically linear. So
I see. I see. So this is the insertion mode, and yeah, I think explaining each bit of HTML can take months
Definitely.
or years.
right. So
let's go to the next things. So which is the next part? So we constructed the DOM tree and how the
DOM
rendering is done.
yeah, so let's see. Let's move on like a CSS file.
Okay.
So renderer CSS. Oh wait, and the token.
Token RS. Okay.
This is a tokenizer for CSS. We also input is CSS string.
Oh, very simple.
And
it only
yeah,
has
it's very
150 lines
simple.
because it's tokenizer.
Right.
And token CSS.
CSS
OM.
Yes. A CSS is a CSS object model. I think. Yeah, it's kind of like a different tree. Like it's similar to DOM tree, but it creates like a DOM tree like tree for CSS.
And the map between them.
Yes,
or
right.
applying the object model CSS OM tree to HTML DOM
Right.
tree.
Yeah, after like parsing CSS, we combine CSS OM and the DOM tree into a layered tree, and we like paint layered tree to the like application.
Ooh, it's complicated.
HTML is pretty complicated.
Right.
Yes.
I see.
Yeah, that is also very defined in like a spec.
Because
Different in the different spec.
the CSS object model spec.
Right, the different one. That's very very defined.
I see.
For example, let's see.
CSS 3 spec or something?
Oh yes, there are tons of applications.
Yeah. So
Yeah.
Right, and there's
Maybe-
different levels, right?
Right.
So which one should I check?
I think there is a link in my code. Can you see my code? Like
Okay. Where?
The top-
This one?
yeah, for example, like this, or a top level one.
Okay. I see.
Yes, that's a
That's a
Pardon.
syntax, right?
right. That's a
Optimization.
spec I
Right.
prefer.
I see. This diagram.
Yeah, and this one is also defined sort of as a English parser, right? Pretty much.
Right.
Oh.
Yeah, this spec like describe how to make a tokens for CSS, and I implemented like for example, consumer token function, consumer comments function, and consumer numeric token functions listed in the left side table. Yeah, that one.
Consume comments.
For example, yeah,
So-
that is one function in my code.
I see. So all the steps are well defined, and so you implemented them as to follow the spec.
Yeah, just follow the spec.
Comment.
No comment.
There is no comment.
Comment is
I
not
think.
supported
I
yet.
see. I
So
see.
maybe consumer token.
token.
No.
Token.
Oh, this is a
Function. Function
consume.
name is snake casing. Yeah.
yes.
Last, I forgot it. Consume token. There is
Not
no
a-
consume token.
Consume
There is a consume selector.
selector.
Consume selector.
Yes. Maybe we can see like a consume selector one in the spec.
Consume.
I hope. There's no.
And because this is Rust, of course, you can use all the handy match blocks to select different tokens you get and build the parser that way, right?
Where is it?
Right. Wait, selector.
It looks like there is no consumer selector. Because it's a tokenization, and selector is an idea in parsing, I guess.
Yes.
Ooh,
Selector.
Qualified rule, maybe?
Clarified rule.
Oh yes. Oh
I
yes.
see. Yes.
Selector
So,
is
mhm.
yes kind.
Kind of qualified rule.
Yes, exactly. So in this spec, the selector is called as like a qualified rule, but in the selector spec, like there's another spec for like a selector, so there's a term selector. But like in the spec, the spec use a qualified rule. So it's really complicated.
Yeah, and I think if we follow all the namings in the spec, then the code will be messy. So yeah, it's a good. I think there is no one by one connection between them. But thanks Asami-san. Very helpful
Yeah,
comments
thanks
here.
to my previous me.
Qualified rule. Yeah, here's the link.
Yeah, I wrote the comment. I forget it.
Yeah, thank you for thank for past Asami.
Yeah, as we can see in the comments, so most qualified rules will be style rules, whereas a preview is a selector, and the block is a list of declarations. I see.
Okay.
Oh,
Okay.
wait, and like besides style rules, like what are the other kinds? Are they like the media queries or things like that?
Oh yes, I think so. Yeah, media query is one with the qualified rule.
That makes sense.
Yeah.
Media query is maybe like a different spec, so we don't see we don't see that in this spec.
I see. So qualified rule, the definition of qualified rule is depending on other specs, and
Yes,
maybe
right,
the CSS versions.
CSS has multiple specs, so it's really complicated to like understand what is a correct behavior. So it's hard point.
Yeah, I think we need some knowledge and experience to read the spec correctly. Yeah. Wow.
But yes,
You were doing front-end engineering, right? So you're very familiar with all that.
a little bit.
Yeah, we are not front-end engineers, so we don't need. Actually, Asami-san needs.
Yeah, I was like a front-end engineer like before.
And I think, you have a chance to write spec itself, right?
That's so cool.
Yeah, if I have a chance, I will do that.
I look forward
write
to
a
see
spec.
your name in spec. Anyway, so
Yeah, so CSS was like a very simple rule, like across this CSS tokenizer and the CSS object model supports like a simple class and element name and ID. That the selectors currently supported.
I see. And so after doing this process, the CSS object model tree is constructed, and
Yes. And we moved to like a layer 3, combine to like a DOM tree and a CSS tree.
where the render tree is
Layout.
Render tree.
Render
yeah,
tree.
it is. So okay, render style and
Yes, we create a new tree, which includes like a DOM information, like a node information, like a kind of like a element information. Also, like a, for example, height, width margin or something like that. And where should we put this element into the window? So a kind of information is stored in this tree.
I see. So every information needed to render the HTML page is
Right.
stored into, or not render style, I guess. Maybe there is a render node or something. I see. Render object.
Yeah, render object is a node, the tree, and it has a style. Render, which is called render style, and the render style has a like a CSS information. Example, position.
So it has style and positions and render object as a child and
Yes.
children, and node kind is the same thing in the
DOM tree.
DOM
The same.
tree, I see.
Yeah. For example, like what kind of elements or like a the string element, string nodes, or the.
Oh, that's the standard one.
Okay.
That is easy.
What is it?
So if you want to make if you are trying to make a better standard that replaces all the other standards, it will add another standard into the pile of
So
standards.
you have more standards.
Sure, sure.
There are tons of standards in this world.
That's what we are doing.
Right?
That's our work.
Yeah. We are making new specs as our job. Yeah, that's a render tree.
I see.
And after we construct render tree, we just print to the window buffer.
I
The
see.
window buffer is a kind of like I don't know how to say sakaime. I forget the
The
boundary
border,
between
boundary.
boundary between our application, my application and the Hikalium's OS.
yes. Where the paint logic is implemented?
Source GUI.
I see.
Yes,
Yes, the source
that's,
GUI. And yeah.
and the
this-
window buffer is a API Hikalium's OS provides.
Yeah, I
so-
made.
Application side can use window buffer. Is that the name is correct?
Okay, and then you have like drawing commands.
Yes,
or
window
something like
buffer.
Yes.
Yeah,
And the window
here.
buffer provides like a lot of API to draw like a lect or something.
that? Cool.
Yeah, you can see liumlib is imported in second line and
Why? That's the boundary between our application and the OS.
And yeah, I wrote this part.
Yeah.
Window buffer. Actually, this API is very interesting because I wanted to. Actually, the binary is compatible with Linux, but we don't want to interact with Linux-specific GUI things. So I decided to store or share the window buffer between operating system and application in bitmap format. So if this application is executed on Linux, it will produce a bitmap image of the rendered window. So you can debug the application on Linux as well
When
too.
you say bitmap, do you mean like a raw image or literally a BMP file with a header and everything?
Literally bitmap. So you can see the header embedded in this code. Where's the header? I think I made a header, but
Yeah, I think it's interesting like idea. Yeah, we can see like a
there it is.
bitmap.
This is a signature, yeah. That's cool.
yeah, debugging is very important, right? So
Yeah. You don't wanna like always run all the code on the target. You wanna be able to test it in your development environment too, right?
yes. So I think this API is good for portability, but limited portability. And I think we need to redesign the APIs once we want to if we want to support GUI interactions like quick clicks, quick events, and other things. So yeah, but this is the current interface. So now, and as you can see, this code paints the direct content.
Yeah, that's our API Hikalium provided.
Yes, but where the HTML content is painted, I think it.
Self. Wait. Oh, currently only like a direct is supported in. So
Right.
we can write any text in our browser.
Yeah.
Right.
Where the code is called based on CSS tree.
Oh yes. The source renderer mode file. Oh wait. Source renderer mode file is
I see. Print render
called-
object. This one?
No. Not that one. Wait.
Mm.
Can you see like a render function? Oh yeah. Oh, sorry. You're correct. Render tree paint is
Render tree paint.
59. Render tree paint. Yeah.
Here.
The function paint.
I see.
Render tree.
So the paint call is implemented in render tree node. Lium source. Not lium.
Render layout.
Render tree.
Render tree. And the paint.
I see.
Paint. Yes, somewhere.
To do support. So many to-dos.
Yes. So.
And this is the only part I call it.
Yeah, direct is
I see.
API currently supported.
I see. Oh, so this is the most bottom part of the browser.
Application layer, right?
Now the direct is implemented in
the hikalium side, and
Yes.
it will call like a system call and tell what application want to do to like a OS.
Yeah, here's the direct implementation, and I don't like this behavior of was it binaries? Maybe it is changed a bit. No problem. Forget about it. And
Maybe we will see direct. Where is
direct.
Yes.
And why? How to cancel the searching? I forgot. Just press enter. Okay. And it will paint the buffer, and after writing pixels. Current implementation writes each pixel, and I think Flash is called separately. Here.
Yes, it is another function.
Yeah.
To Flash.
Here's Flash. I think this you can see the text, but here's a Flash window buffer Flash. So this will flash the buffer, and Flash means making a bitmap image of memory and notify OS about the update. So where is FLU? Yeah.
Where is it?
Flash window buffer. Yeah, so it is implemented. It is abusing msync syscall. So if you because if the so the buffer is implemented as a file, memory mapped file. So if you create a window, it will open window.bitmap file in this current directory. And if in Linux, it will open a normal file, but in my operating system, it will that bitmap file will be mapped with the window buffer allocated in the operating system.
If you literally open a file called window.bmp, it becomes a window like automatically.
Yes.
That's awesome. It's like Unix, everything is a file, but even more.
Yes. Everything is file.
The UI is also
The UI is that's great.
Window is file. Okay, then let's check the operating system side implementation. So in liumOS, it is implemented in C++, but what was the file? Cisco RS? Here's not the RS, Cisco CC. And let's check. msync. Yeah. So here's the msync and open. Where is the?
I'm not familiar with like msync Cisco. What kind?
So msync Cisco is to ask operating system to sync the region of the memory, and usually it is used with memory mapped file. And if you issue msync, then the content will be written back to the backed file of the memory mapped of the memory mapped region. So yeah, it is similar to F-flash or something. So just flashes the data into file.
I see. Thank you.
Okay, so if you open here it is. If you open window bitmap, then just to return file descriptor 7. Currently, there is no file descriptor management. Most of the system calls are returning fixed number of file descriptors. So it is, definitely it needs some improvement, but it
works.
It works.
Can you
So-
open more than one window?
No,
Not right
not
now.
for now. Not right now. Not right now, unfortunately.
Yes.
But I will fix that soon, or re-implement it soon in my new operating system. So yeah.
Oh wait, can we?
Mhm.
I think we can open multiple windows right now. For
Um,
example, when
if we can open multiple windows from multiple process, but if from a single process you
Oh,
can
I see.
only a bitmap, only one window, because file descriptor namespace is separated on the process boundary, right?
Yeah, okay.
So,
I process.
so process number 7 is only valid in this process context. So then, if you after calling sysopen syscall and with opening and application if application tries to open window bitmap, and application will get file descriptor 7. And next we will map that file onto memory. So mmap syscall is here. So currently, this mmap function is implemented only for window management purpose. So here's a check if the file descriptor is expected or not. And after that, we will allocate window frame buffer and for now, it only allocates the window buffer, but not window itself. And I think window will be created on msync. That is not a good design. I think it's a historical reason, I guess.
That sheet, the window sheet
Yeah.
is like the window.
Yes. So
The
window
buffer,
sheet.
right?
Yeah, window sheet represents the window buffer or one sheet of the in the window system. Here's the to-do. Exactly, I said. Anyway, and so here we will allocate sheet buffer and set the buffer into initialize the sheet with the buffer allocated in fopen syscall, and we will copy the buffer given by user into this backed buffer and do flash to display the content. So which way should we go? Do you want to dive into flash or going up to inside the operating system?
I'm kind of curious about the memory management, like the
Okay.
paging and all that stuff.
Okay. Then let's check the memory management stuff.
We
Actually,
allocate Connor?
yes. And actually, my operating system is very unique because it supports non-volatile memory.
Oh,
Have you had non-volatile memory?
I've never used it. I know like NVDIMMs and stuff.
Yes,
Yeah,
NVDIMM.
I've never used it. I know they're a thing, but I don't have any.
Don't worry, I will explain it. I was researching about NVDIMM when I was a university student, so this is my my area of expertise. Actually, I implemented my operating system for my research because I think in my opinion, modifying my own operating system is easier than modifying Linux. So that's why I implemented those features in my operating system. And as you can see, here is a pmem.cc file. It is this code is for managing the persistent memory, the objects on the non-volatile memory, and those these functions are called from memory map things. And where is the memory map? I think the last time I touched those codes are multiple months ago. So I think let's check.
Yeah, it happens.
Let's start from the boot. I think chasing the code from boot is the easiest way to understand the behavior.
Okay.
So and where is the so first loader is implemented here, and loader will load the kernel. So loader will be launched from the UEFI. So
this runs using boot services, right?
Yes, it works. It uses UEFI's boot services and load all files onto memory and just exit from boot services. And also we retrieve the address of the frame buffer from UEFI boot services. Sorry, and just load. Where is the road? This code continues more and interior management. So here is the load kernel F, and it will transfer the execution to kernel. But before jumping into kernel, let's check the memory management initialization. Here's the init DRAM management, and
Luna says make sure to drink water, make sure to hydrate. Don't forget.
Oh, and yes, and this function takes the AFM memory map because memory. We don't know how much memory is installed in the machine. Only EFI knows about that kind of information. Actually, not only EFI, but ACPI knows the information, and EFI provides the interface to read them. So we can get the information from UEFI and initialize the DRAM management. And I think the DRAM management is implemented in where? Oh, in this file. Okay. And into DRAM management is like this. And so physical page allocator is the class that implements the page allocation. So we will initialize the allocator to manage all the DRAM regions. And available DRAM kilobytes. Okay. And set the DRAM allocator into the loader info here. And the physical page allocator is very simple. Actually, this allocator does not support free for now.
Oh.
What? Oh, I have some delivery, but ignore. Please ignore the.
You can check it.
I don't want to. I'm not good at.
You can take a break if you want.
No. I can do. Where? So I wanted to check the how the physical page allocator is implemented. So where? Physical page allocator. CC.
Allocator looks.
I think the header file is better. Physical page allocator H. Here's the physical page allocator, and just allocate the memory from the buffer. But how they are managed? I forgot what algorithm is used here.
Looks like there's a free info that like have
yes.
like a
So
text pointer.
So each region of the free memory, each contiguous region of the free memory has a free info at the beginning or at the end of the region, and it has the information about how many pages are free in that region, and it only manages how many pages are free now. So it likes it is like a watermark allocator. So you can't free pages for now. Okay. And
Do you have a plan to implement free?
I already implemented free in new operating systems. So
Okay,
yeah,
nice.
yeah, those code will be replaced by them. So we will not implement a free in C++ because C++ is
Memory management in C++.
yes.
Wakaru.
After I got used to Rust,
Yeah.
I don't want to write C++ anymore.
I agree.
Because, yeah, Rust is very nice.
I got used to Rust for this kind of stuff and to D because Inochi2D is written in D and it also has a garbage collector. So I got used to D for like graphics programming, and now it's like I don't want to use C++ for anything.
Yeah, that's so. Yeah, reading C++ is also annoying, especially if the last time I touched this code is months ago, and I was okay. Let's go back to low latency and
So now we have a locator.
Yes, memory allocator is initialized init memo. Where? Okay. So DRAM management is now initialized, and init double buffer initializes the double buffer for the VRAM, which is previously initialized. Also, here's a panic printer. This is very interesting thing because so if the kernel is panicked, I think most of the kernel structures are they may not be valid. So I implemented a separate printer for panic printing to make sure that we can print out the messages even if the most part of the kernel is broken. And it is very important to debugging the memory-related issues because memory-related issues can break the kernel memory easy. And it's hard to debug.
It's like early con on Linux, which is sort of like before everything else is initialized.
Yes.
Right.
You need something low level so that it always works.
Like serial port.
Yes.
Oh, so
Linux takes a similar approach. Oh, sorry.
Yes,
Okay, go ahead.
Okay. So after that, the main console is initialized. So console here means that you can print text and you can take input from it. And so after that, we will set up the stack for kernel and load and initiate the GDT, global descriptor table. If you know about x86, it is basically the information about the memory protection and other things. And also IDT is the interrupt descriptor tables. So interrupts are initiated here as well, and also initiates page tables again. And after that, just load the liumOS, which is the main part of the kernel, and and just called load kernel F, and it will load where F H C C, I guess. Load kernel. Yeah. So it is very simple. Just load the mapping info from the F file and just do the mapping as provided. So the address.
So is it relocatable in physical memory?
No, actually, the kernel binary is not relocatable, but it is already relocated to the higher half of the address. So we can directly use the mapping information without doing relocation.
So the virtual addresses are not relocatable, but the physical ones are, right? Like you can map it anywhere in RAM, or is that also not relocatable?
What do you mean physical?
Like the kernel can be loaded anywhere in physical memory, or does it also need to be loaded at a specific place in physical memory?
Kernel can be loaded anywhere in the context of physical memory, but in the specific virtual address. And those allocation is automatically done in the allocation function. Let's check the allocation function. I think how. Okay, let's chase how the. So there is no demand paging yet. So the pages are mapped on the allocation. So where was that? EFI, RS? No, CC. So in EFI, CC, we have load. Oh, where is load kernel? Not EFI. elf.cc.
There are tons of files.
I made this kind of mistake so many times. Anyway, okay. So load kernel elf we call here load and map function will map the it also takes the allocator. So we are specifying the DRAM allocator here because we have two kinds of allocators. One is DRAM allocator and another is PMEM allocator for NVDIMM. So,
right. I mean, that makes sense, right?
Yes. It makes the code more complicated anyway. But load and map segment.
Currently, is it currently used for like QM? When we make long, when we execute make long, so is it useful?
For what?
Use key allocator. Sorry,
PMEM allocators.
PMEM allocator is it
QEMU?
used?
Yeah, they're used even if we are in QEMU because QEMU has the emulation of the NVDIMM, so you can use
I see.
You can use fake NVDIMM on the QEMU.
I didn't know that.
Yeah, I think most people don't know about that feature. So if you see the QEMU args here is memory backend file. Yes. So if we launch our OS in QEMU, it will get 2 gigabytes of 2 gigabytes of NVDIMM. So PMEM allocator is also initialized in QEMU, even if in this case if we do make run on this machine. Okay, so load and map segment will do the mapping and segmap is called, and where is the map? I think it is implemented in the header file of this. No. Here is another complicated things because my operating system supports process checkpointing natively using NVDIMM. So the process context.
Sounds super cool.
Yes.
That was your research topic, right?
Yes, it was my research topic. Unfortunately, the research paper is only published in Japanese. But if you are curious, let's check that.
The research about like MV.
No. PDF here. Yeah.
Nice.
You can see those there.
Maybe
that's
people
super
can
cool.
translate.
But also,
That's
actually,
why we have NVDIM support.
and I ported that feature into Linux. So,
Oh.
but it is very ad hoc implementation. Don't expect if it works with every application because. Application checkpointing is a very difficult problem.
Yeah.
You need to this my implementation does not support file descriptor preserve or something like that, but it only supports the memory contents and the execution state of the process. So, and you can check the my YouTube because I have the demo here. And okay, I will skip that. Okay, skip trial. So this is a bit old version of liumOS, and you can initialize the persistent memory and you can see this program is calculating the pi value, and in the middle of the execution, I killed QEMU and started up QEMU again. And if we run pmem restore, pmem ls shows the saved context, and if we run pmem restore, it will resume the execution automatically.
Cool.
How do you know, like, if you can kill QEMU at any time, then you're restoring like a previous snapshot?
Yes, it is doing some kind of periodic snapshot. So you can change the interval of the checkpointing, and also this also cooperative checkpointing is supported. So application itself can request operating system to checkpoint itself. I think using the latter way is more efficient, but I wanted to make this feature transparent, so I also implemented periodic snapshot as well.
That's super awesome. I could use that for like when I have something running calculating something, and it's like, what if it dies? Would I have to shut down or something? And it'd be to just like save it to npmem and restore and just have to keep running.
Yeah, thanks for saying that. But here's the downside of using that feature, because unfortunately, non-volatile memory is slower than DRAM.
Yeah.
And also, snapshotting needs the duplication of the execution context or the execution state. So it's very, very heavy. Like I think it's twice slower than not twice, or 10 times slower than normal execution, I guess. I forgot how much the execution was slow, but
also the hardware is still expensive, right?
Right.
Yes. Yes. Unfortunately, true. Because NVDIM itself is cheaper than DRAM. If we the cost per bytes is lower than DRAM, but the machine supports NVDIM is very expensive.
Right.
So yeah, that's the problem of using NVDIM. But I bought that machine because I wanted to experiment it in my home. It was expensive.
It's pretty much like servers and workstations and stuff, right?
Yes, it only NVDIM is only supported in Cascade Lake CPU, and yeah, it's only Xeon CPUs, and so Xeon Silver something is the only the cheapest one I can get.
So I have a technical question, but how stable is NVDIM when you like change the DIMMs around and things like that? Like, does it is there any guarantee that the data is going to still be readable if you like change the layout or put it in a different machine, or is it pretty much don't touch it?
Good question. I think the answer is don't touch, don't remove them. But actually, PMEM supports hot plugging in some platform, and it is because PMEM is designed to used in data centers, and but hot plugging DRMM is what?
Yeah.
I think there is no actual hardware supports PMEM hot swapping, but
It's maybe for VMs or something.
Yeah, but technically the spec says they support hot plugging, and but yeah, in the software side, I think they can't they are not good at handling that situation
And like
at this moment.
even if you shut down the machine and move the stick to another machine, is there a guarantee that you can read the data, or is it different if it's like the layout and the memory map and everything?
If you replicate the same layout on another machine, I think the data it is guaranteed that data is preserved. But if the layout is changed, not sure. Ask Intel folks.
Because I imagine if it's the same as normal memory, I guess it would like interleave between multiple NVDIMMs.
Yes. So yeah, it's difficult to use in the real world, but I think NVDIMM is very interesting hardware to do some research on it. So if you're curious, please ask me about anything about PMEM.
What's sorry.
Go ahead.
What's the actual storage technology that they use? Because it's not Flash, right? Is it like
3D Crosspoint.
Oh, 3D Crosspoint. Oh, okay, that one.
Yes, that one.
I need to read up on that again.
Yeah. I think we have or Intel has 3D Crosspoint SSDs, but they are please make. I think many people were thinking about they are same, but they're not. The storage, the chip. I think how to say that the storage element is itself element is same, but 3D Crosspoint SSDs are only supports block access. Not the cache line size access.
It's not RAM, of course. So,
yes. So if you want to play with NVDIMM, you need to make sure you ordering the NVDIMM, not the Optane SSDs.
Do you think it is possible to replace all SSD with NVMe in the future?
I hope so, and my hope is that NVDIMM replaces all the DRAMs and I want to make a laptop which only has NVDIMM on it.
Oh, did you make it?
No.
Sorry.
My hope.
You want to? Okay.
My dream.
Maybe we should make it. We should like hack something together and make a laptop that supports.
Yes.
Nice idea.
I think we can do that.
Yeah.
But
do they have them in like SODIMM form factor?
No,
just full DIMM.
Yeah, they only have full DIMM form factor
Okay,
for now.
Then we need to make our own SODIMM NVDIMMs.
Yes. So we definitely need help from Intel.
I mean, I can make PCBs. I can design PCBs. We can make
Really?
we can do that.
Wow. But
PCB? Sorry, what we said?
PCB is printed circuit board.
Oh, okay.
So wow.
I think we can think about that. Maybe we can try something.
But the problem is that I think the also chipset support is needed as well, and only specific CPU supports the NVIDIA. So you need to drive Xeon CPU with your PCB. I think it is very difficult.
It sounds interesting to investigate, though. Maybe because
Right.
maybe there's something we can do.
Yeah, something we can try at least.
Yeah.
Yeah, let's do that if you're curious. I want to do that.
I'm curious about like the if it's possible, or even like on AMD or something, because AMD is like nicer about weird stuff. So I don't know. I'd have to think about it.
But currently, I think NVIDIA is only supported in Intel platforms. Please make everyone please make NVIDIA more. I think no one uses NVIDIA. Not no one. Definitely Google uses NVIDIA, I guess, and other companies, other data center. I think other companies like using providing the large scale hosting service is using NVIDIA, but they are not using NVIDIA's persistence. Mostly, I'm not sure. I'm not sure.
Do you mean like there's no use case for personal usage now?
No, not personal usage, but persistent. They are not using the persistency or non-volatile
so they
characteristic.
just use it as cheaper memory that is faster than SSDs, but slower than regular memory?
I think so.
That's interesting.
Yeah. Actually, Google published a far memory paper, which I think uses. I think it is it's not a good idea to mention it from me because no. But anyway, here's the paper. So yeah, it is. I'm only talking about the public information. So yeah. Okay, let's go back to
move to the next topic.
So, what? So.
What did we talk about?
We were talking about the loading. How
there are
Kernel
two
is
kind
loaded.
of architectures, right?
Yes. We diverged a lot, and parse program header and so map.
Vincent, using persistent feature is hard because of the volatile CPU cache. Yeah, right. You'd have to flush the cache, right, every time.
Sure. Yeah. But here's the interesting thing is that the NVIDIA feature availability is exposed via ACPI table, and ACPI table has feature bits, and ACPI here's let's check ACPI spec. I want to show you the interesting feature bit in the ACPI because ACPI the NFIT is the non-volatile DRM firmware interface table which exposes feature of NVIDIA and the platform capability structure shows what type of things are supported, what features are supported by this platform, and interestingly, where interleave structure, SM BIOS, NVIDIA control gene struct, NVIDIA block data enumeration, flash hint address structure. Sorry, what? I think.
Are you searching for?
So here is wait. Here. CPU cache flash to NVIDIA durability.
I was gonna ask about that. Yeah, like that should be possible, right? If you have enough like reservoir power,
if you have supercapacitor or battery in the machine, then it is technically possible to flash the CPU cache into NVDIMM. So
I think, honestly, I think you wouldn't even need a battery or a super cap because the CPU cache is tiny, right? So I think even just the power supply cap is probably enough. Like it should take like a milliseconds, right?
But these days CPU cache is very big, and it is difficult to guarantee that they are written into NVDIMM instantly. So
what's the write speed for NVDIMMs approximately?
It is very it's very good question because the write operation is cached, queued on the controller, and if we used up all the buffer, the write will be very slow. I think. I think recently some researchers published the PMM performance evaluation, but where was that? This one, I think. Now I'm introducing about the NVDIMM because I really like about operating system. Maybe this is not the one. DRAM random, DRAM sequence, obtain random, obtain sequence. So bandwidth will be very small, and bandwidth and latency will be. Where is the latency? Tail latency is really bad.
It's the microseconds, right?
Yes, microsecond.
I mean, the bulk write speed was how many gigabytes per second? There. Sort of
Is
so.
there? I forgot the latency bandwidth, latency user evaluation. Is there any bulk access performance evaluation? Here's a blog. I haven't checked this. It's just an article. Anyway, I think.
Sorry for the distraction.
What I wanted to say is that unfortunately NVDIMM is very slow. And
But
performance
it's
is
still faster
unpredictable.
than Flash, right? So.
Yeah. It's faster a bit than Flash, I guess. I forgot the results because I graduated from university multiple years ago. But anyway, yeah. So it is very interesting, and here's the CPU cache flash feature bit. So if the machine supports CPU cache flash feature, then we can easily achieve the persistency without manipulating the CPU cache manually from the software side. But I never saw such a machine that supports this feature. So if you have a machine supports this feature, please let me know. I want to touch that machine.
I'll let you know if I find one.
Yeah, please. And okay. So here's the mapping functions, and okay. The allocator is specified in the map functions. And sorry for going back and forth multiple times. I have so many things to talk about. Here's why explained about the NVDIMM things, because and so the data structure used in this operating system is a bit weird because we need to duplicate the execution state, right, to support the snapshotting. So the execution environment. So let's check the execution. Let's check process context. Process first. Process is persistent function, and which means that if the process is persistent, supports the checkpointing, it returns true. But anyway, yeah. So, and the execution state is duplicated in 2 copies, and the copies are here, execution context. No, not this. Right. I forgot how it is implemented. But so execution context, basically the execution context has all the information needed to needed for the to execute a process. So it contains the mapping of the code, data, and stack and heap, and also it has the CPU context in it. And so
do you have always multiple execution context, or
no, only for the processes which is launched as a persistent process, which is so only the processes enabled the process checkpointing feature is enabled.
A specific mode, right?
Yeah, but the data structure is reused. So if the process context if the process is ephemeral one, non-persistent one, it will only create one execution context. But if the process is a persistent one, then execution context will be created. 2 execution contexts will be created, and they have and so at least one execution context contains a valid state on the last snapshot. Anyway, so even when we load the kernel onto memory, the same process same process structure is reused. So we need to get into this code, and execution context is has all the information, and it has map, I guess, map. Yes, and segment mapping, and map function called create mapping, and create mapping function is provided by paging.h. Paging.h. Create page mapping. So here is the create page mapping function, and it modifies the page table and maps the physical page into virtual memory. And it also takes the allocator, right? Because it allocates the pages for the page tables. And the
and you support like 2 megabyte pages?
It supports 2 megabyte pages and also supports 1 gigabyte pages.
Nice.
I think. Yes.
I see now 4K pages.
I think I implemented at least the paging infrastructure supports the gigabytes pages, but
I think someone said even macOS doesn't support huge pages, so that's already more than macOS. I don't know if it's true or not, but someone mentioned that at one point.
Yeah, unfortunately, what was it? 1 GB paging? Was it 1 GB paging? I forgot how to. Where is the template thing?
C++.
Yes,
Uh,
I don't like this, and yeah, I wanted to make this code generic as much as possible. That's why those yeah. Okay. PML4E. Okay. So allocate our pages and create page mapping. So of course it supports CL flash operation. CL flash instruction is an instruction for flashing the CPU cache and make the data persistent in the non-volatile memory context. So yeah.
so this is making the page tables themselves persistent?
Yes.
Oh.
So the page table is also stored in NVDIM.
That's cool.
I think no one stores a paging table on NVDIM before. I think this is the only operating system stores a page table in NVDIM.
That's really interesting, though. It makes sense, right? And you can just point, the CR4, and it's there.
Yes,
right?
yes. Then everything is restored. It's cool, isn't it? So anyway, I thought 1 GB mapping is supported, but it looks like it's not supported. I thought, oh, wait, create page mapping.
I saw the comment that says.
I see.
Oh, you.
Please go ahead.
I just saw the comment like a 2 MB.
I think the mapping function is implemented here, not in the header file, but in the C file, and oh. Oh.
There's the support flag.
Yeah, it checks the I think I implemented that feature once, but I noticed that many platform doesn't support the 1 GB mappings. So I rewrote the code to only to use up to 2 MB mappings. It looks like so. Wait. Direct map 1 GB pages. This value is not used. What? I guess it only is for the debugging purpose. And yes. Page attribute, create page mappings. PML4.
Maybe you started implementing it and then it kind of forgot about it.
Yes, forget about it, I guess. Yeah, this kind of thing.
I know that feeling.
Many times.
Yeah.
Yeah, it happens. Sorry. anyway, so
That's low-level programming. You start thinking about how many things you want to implement, and then you're like, I'll do that. And then I forget about it. Yeah.
because I wrote everything in this in this operating system. So if you wrote this amount of source code, you will lose the control
it's hard
of
to manage.
Stack Overflow.
Yes. my stack in brain is overflow.
Maybe you should write a to-do comment in the file.
They have a lot of to-do comments already.
Okay. You already have.
Yes. Like this. Oh, not so much. Anyway, let's go back to the loader. So now kernel is loaded. So let's go to the kernel source code. Kernel CC is the implementation of the kernel. And yeah, here is the kernel entry function. This function is set to the entering point of the L file. So the execution will be transferred to this function, and it will reinitialize the allocators again because the allocator we initialized in the loader are for physical page allocating. So physical page allocations. So we need virtual page allocations for kernels. And so this function initializes the allocators, which is used by the kernel, and also persistent memory management is initialized again. And okay.
I like that one. Disable any. It's like it's x86, right? So you need to disable all the.
It's x86.
Like 80s features to get a modern machine.
Yes. So x86 is a pile of legacy history. So we need to disable old ones and enabling new ones. So most of the operating system is doing the similar things. I think you are doing your operating system doing the same thing.
Turn off the gate A20.
Yes, turn off A20 gate. Yeah, like that. And yeah, turn off the 8259 programmer interrupt controller, the legacy one, and enable the APIC advanced programmable interrupt controllers and the IO APIC, and also initializes the HPET instead of PIT. And
Does it happen on? Does it happen on M1 rack too?
Oh yeah, no, M1 doesn't really have any legacy because it's ARM64 and the actual stock is all Apple, so there isn't really any legacy stuff really, because they don't need to, right? Because it doesn't need to be compatible with old stuff.
Right.
Yeah,
And they have a control of the hardware, so they can freely remove or add a new or old features. So
What it does have,
That's
though,
nice.
is it has some features for x86 emulation to make it a little bit easier. So you can actually switch the M1 to use the x86 memory ordering mode, which you can't on most other ARMs.
What? Android mandates PIC even on i386? Really? That's crazy. From the comment.
The concurrency model then is different in ARM and x86.
Yes.
Yeah, so the M1 can pretend to be an x86 for that, which is pretty fun.
For supporting, for better supporting of the Rosetta 2, the
Yeah, exactly, yeah.
Support.
And it also has, it's really funny because it has support for some flags that SSC has that Neon doesn't. And then Apple ARM added those flags in a later version of the ARM64 ISA, but in a different place. And so Apple calls them by the name in in SSC2, and then ARM used like different bit names, so it doesn't sound like they were copying it.
Wow,
Yeah.
interesting. So yeah, implementing operating system on x86 is not recommended because this kind of
I once
things
did
are
like
needed.
I did just a toy bare metal app for x86 once, and I remember it's like you need to do all this stuff just to go to 64-bit mode and to like
So, but I like x86 because the first architecture I saw is x86. So yeah.
Wait, we were talking about a different pick. People on the comments are mentioning. Mary says, "Do you check the HBit max frequencies and all that?" Yes. It checks the HBit frequency as well. Because HBit provides the HBit. Oh, wait. Yes, HBit provides how many counts per second. So it is needed because you want to measure the time. You want to measure time in the operating system, right? So yeah. Okay. And okay, I think Ridley's making some comments, and I think she's a little bit confused. Like, when we say PIC, we mean the programmable interrupt controller, not position-independent code.
I see. Yeah, it's complicated.
Acronym collisions. And when I was talking about the memory model, I didn't mean the addressing modes. I meant the memory ordering guarantees, like with multi-threaded writes and atomicity.
Right. Now everything makes sense. I see. Oh. So yeah, 3-letter characters and 4-letter characters are all used up in
in IT industry, yes.
IT industries. So okay, let's go back to So basically, here are the initialization of the serial port and the main console, as you saw when the operating system boot up, and now we initialize the root context for the main the kernel process, which it is a swapper in the Linux name, and yeah, after that we just C++ hack here. We are calling constructors here. You know, C++ has constructors, right? The static variables can initialize at the startup time. But in the operating system, you will call the. We don't have any initialization code like CLT, so we need to manually call constructors manually.
Right.
That's why we are reading the liumOS elf again and passing the section header to get constructor pointer array and calling them directly here.
So you initialize static variable manually in the
Yes. So
well.
So you can't use static variables with initial values before this line.
Oh.
And it sometimes causes the weird behavior because those memories are assumed to be initialized in C++ code, but it's actually not.
This is another thing very common in low-level programming, where you're like, technically this is supposed to happen, and the language doesn't guarantee anything, and then you're just like, I know what I'm doing. It'll be fine.
Yes.
Like the mini bootloader is relocatable, and the relocation table is actually like interpret it in C code. So like assembly calls C before the binary is even relocated. And it's like that if the compiler tries to use like a global reference there, it's going to explode completely. But it's just like you shouldn't do that.
Right. Yeah, to suppress that, we need to specify a lot of C flags to the compiler, right? Like the most common one is, I guess, red zone. Red zone is used for optimizing the performance of the, I think, the tail function, local variable usage in the tail function, but it broke the stack in our context, so we need to turning off the and the bug caused by accidentally turning on the red zone in operating system is the broken context after switching the processes. So it is very hard to debug, and without the knowledge, I think it is impossible to notice that the red zone is the issue. Anyway, so we have many I mean the tips, hidden tips in here. Anyway, okay, now we allow interrupts, and so what are we doing now? Oh no. We are not allowing the interrupt, but we are disallowing interrupt here. And so we are initializing the critical things like merge process and GDT and IDTs. Oh, and the keyboard support is initialized here as well, and the mouse supports, and also timer handler is initialized here, and PCI devices.
That reminds me that when I did that little low-level bare metal app, and I used the PS2 mouse, and I tried to use.
If you use QEMU to develop operating system, you will find multiple bugs in QEMU. I submitted multiple patches into QEMU because I found QEMU is very buggy.
Yeah, it's like pretty much every hardware virtualization software is just enough to make the main OSs work, and then everything else is like nobody cares.
Yes, true. So, one thing I found, one unimplemented feature in QEMU was this operating system supports USB. Actually, none.
XHCI.
Yes, it has XHCI driver, and
that's great, actually.
Yes, and XHCI has a command with no op command, and no op command is used to check if the command queues are working correctly or not, and so it just queues the behavior of the no op command is just if we submit the no op command, then they will just reply that the command is finished. But QEMU didn't implement it because no one uses it.
I don't know why, but I'm getting the feeling that in a previous life I had something to do with the QEMU XHCI implementation. For some reason, I'm getting the feeling that it's my fault or something like that. I don't know why, but I'm getting that feeling.
Your feeling is nice. No problem. So yes, so be careful and be careful about I mean, not your if you see your operating system is not behaving correctly, it is possible that QEMU it's a fault in QEMU, not in your operating system. That is very important point.
That's really hard to debug.
Actually not so hard.
Really?
You can attach GDB directly to QEMU, right? So it is very useful, actually, even if we are not debugging QEMU, but debugging the device drivers in the operating system, because we can put arbitrary breakpoint in the device implementation in QEMU, so we can cook and we can notice we can check how device works in with the driver we wrote. So yeah, it's very useful, but it's a bit tricky. Anyway, so the important thing here is enable syscall here. Enable syscall here, and this is implemented in syscall.cc, and enable syscall will set the CPU flags to enable the system call. So yeah, syscall instruction
right,
is
you
very
used
special. Yeah.
That one, the new one, right? Yeah, not the int 80.
Yes, don't use int 80. Syscall is more efficient than int, but
Is it newer version?
yes, it's
Okay.
only it's early days x86 doesn't have syscall instructions, and AMD implemented this the similar one. What was it? Syscenter and Sysrave, I guess, and those and Intel did the same thing for the system call.
I see. So that now we should use Cisco instead of
Yes,
int.
yes.
Okay.
Because why interrupt is heavy is because they save all the registers, all the process context, because if interrupt happens, all the state should be preserved.
Oh yeah, we should store all state to
Yes.
exact place. So
Yes, but
it takes time.
But if you use syscall, we know application is aware of syscall, and so if we define the calling convention for syscall, then we can destroy some part of the execution context, like registers. So that's so using syscall instruction minimizes the cost for saving the context. So it only saves the instruction pointers and the stack pointers and so on, the minimal information needed to switch the context, and I guess the execution mode. Okay, so by doing this, the system call handler is registered, and Asami system call handler is implemented in assembly. I think this is, can you see this? Asami syscall handler, and this is implemented in syscall handler. Syscall handler S, and it will call syscall handler here. And syscall handler is implemented in syscall.cc. So it's going back. It goes back to this file. Syscall what? Not here. Huh?
Oh yes.
Syscall handler here, and yeah. So just handle each syscalls here. We already checked some of the system calls here, so I think.
Oh, finally we read the msync stuff.
Yes,
here.
finally we came back to this.
Finally go back to the msync stuff.
Yes.
it was a long journey.
Close the loop. Yatta!
Yatta! So if you call msync, it will flush the flush the buffer and print and copy the content of the buffer into VRAM, and the content will be displayed on your screen.
Nice.
It was a long journey.
Finally, we reach here.
Yes.
Yeah, this is like a boundary between application and our
Yes.
operating system.
Yes.
And we saw the code from bottom to like a system core, and the top from top to system core. Yeah.
Yes. So, do you have any questions?
Yeah, I saw lots of comments in there. Out.
Yeah.
Yes, thank you for the comment. long story.
So I have a question. Do you use page faults for anything, or is everything, or is that like fatal? Because you said you didn't support the band paging, so I wonder if you use page faults, like have a handler for that.
Currently, we implemented this operating system has page fault handlers, but page faults can only happen if application accesses the invalid pages, which are not mapped in their virtual address space. So there is no demand paging, so it is only used for protecting operating system from the attack from the application side.
Right.
So the implementation is in the interrupt CC, or maybe exception. Oh, interrupt CC.
Actually, the next thing I was gonna ask about was interrupts, not page faults, but like hardware interrupts.
But
Like, can you,
please go ahead.
tell us how the hardware interrupts are implemented? How you like dispatch them and like go to the drivers?
Good news here is that I think they are registered directly. Oh, wait. Are we using interrupts for devices?
Is it polling?
Actually, USB driver is implemented with polling.
Oh.
But I think the PS2 keyboards are using interrupts. So let me check with this PS2 mouse. Interrupt. Oh. So it looks like it uses interrupts. So here's the inter handler for mouse, PS2 mouse, and so I think this function is used somewhere. What? No. Okay. I think the page this handler is registered in mouse. Keyboard? Let's check keyboard CC first. Yes. Wait. No. I thought keyboard handler, keyboard interrupt is shared between mouse interrupts, but it's not. Yeah, because keyboard interrupt is number 0, but mouse interrupt is last index of the peak. But anyway, and keyboard controller init set. So it directly sets the inter handler to specific interrupt numbers. That's the answer.
And then in the IO APIC, I guess it's just mapped like that, or?
Yes. I think the IO APIC APIC CC, I guess. Okay, APIC CC does that already, like this.
Yeah,
So
yeah.
in the initial stage, they will remap the old legacy interrupt into the,
Yep. PRT index. Yep.
But the idea of IO epic and epics are complicated, isn't it?
Yeah.
I spent multiple hours to understand how it works.
わかる。
難しい。
難しいよ。
It's very difficult.
Yeah. You know, the M1 is a lot simpler. The Apple Interrupt Controller, they have their own. The official ARM one, GIC, is also super complicated. But the Apple doesn't use it. Apple uses their own AIC, and the old version is so simple that even without the hypervisor, you can figure out how it works just by dumping registers and trying things. It's like super simple.
Wow. Good design.
Yeah.
But, unfortunately.
Now they have a new one that is actually, it's not really more complicated, but it's more like magic. So it does things like pick the CPU to send the interrupt to automatically and weird stuff like that. So I don't know, it's very strange. But it's cool though.
It's cool, but overly complicated for ToyOS reference.
Yeah. I think you might enjoy reading the source code to Mini, the first stage bootloader, because it's very similar to this, right? It's like doing a bit of
I can imagine.
Like enough hardware support to be able to load files from disk, but
yes. Everyone doing the same thing.
Definitely. It's written in C though, no templates, and a bit of Rust.
So this is the liumOS, but as I said few minutes ago, I don't want to write C++ anymore. So we are developing a new operating system called Wasabi, because Rust means rust. And which Rust means rusty. The oxided things, right? And it is called sabi in Japanese. So that's why I put Wasabi for the name of the new operating system.
That's funny. That's great. I love good names like that. It's great.
So here is Wasabi operating system. Of course, now it is implemented in Rust fully. So let's check how it is different than liumOS. Of course, this is work in progress, and it only supports it can't launch applications yet. But I will show you how it works. So it supports.
My application will move to Wasabi OS 2.
So
nice.
Yeah, I made this logo. This is Wasabi OS logo. Okay, and
That's really cool, actually.
Yeah, text output works, and also serial. You can get the serial port, and memory management is initialized, and we can run. Testing is a difficult part for operating system, but this operating system has integration end-to-end test, so you can test but I think the integration test is not implemented yet, but it has the memory allocator test. It actually launches the just run make test. So it launches QEMU and it runs the tests. So we can run unit tests on QEMU.
And it's actually the VM. That's really cool that you can do that. Yeah.
So we are using custom Rust custom test framework to support that. And also, not only this, but test. So Oh, I think it is not implemented yet. I thought OS has some. They have some tests. Yeah, here is the global allocator test. So we can. I think it is already run. It was it executed? Font being OS booted. Okay. I migrated the integration test into unit test here. So this test does allocate and free multiple times. So it ensures that the memory allocation works correctly, is working correctly. And okay, let's check the operating system source code. So the source main part is implemented under OS source and main RS. So in main RS, yes, UEFI main is the entry point for UEFI application. And currently, we and I think we will not move. We will implement this operating system as UEFI application. So we will not separate the kernel from the loader because it is easy to implement. And so it initializes the basic runtime and the graphic terminals and the allocators, and after that it just pauses, and main function just prints Wasabi logo. And let's check initialization code. In its OS source init RS and So init basic runtime initializes the serial port and memory map. And by taking memory map, we will exit from boot services. And after that, just memory allocator is initialized. And this is the GUI thing. Wait. Load all root file is also being implemented, but it's not working well yet. And VRAM initialization is also done in where? VRAM. Get VRAM info. VRAM is implemented in a separate file. VRAM RS supports. Those informations are stored into this structure, and the information is taken from the UEFI as using the locate graphics through the graphic protocol. It's better than C++. Definitely. So now this project is still work in progress, and it doesn't have interesting things in it, but I will make this operating system as much as same as much as possible. The same as much as possible with the liumOS.
What's
Sorry.
What's XOR-shift.rs? I'm curious about that.
It's for random number generator.
Oh, okay.
But why? What part uses XOR shift? Maybe it's hash map or something? What? Okay, XOR shift is implemented, but it looks like no one
uses it.
I made this for testing, I guess. I implemented some test code uses random numbers, but and also we will need random number generator at some point, right? Because interestingly, quark rate does not have hash map. It is trivial that the quark rate does not have hash map because quark rate does not support memory allocations. But even alloc rate does not have hash map because hash map is hash map depends on the random number generator, and random number generator is always provided by operating system usually, right? So that's why alloc rate does not have hash map. Yes, hash map, and that's why we will need a random number generator in the future.
Can you get well, I mean, I know the CPU has the RD rand, but can you get randomness from like EFI or some other way, or do you have any kind of standard way of getting like a seed?
I think it is possible. It is possible, but Linux stopped using it because they thinks that they can't trust the random number generator provided by hardware. So, but we can. It is possible to use them. I implemented. I implemented reading that random number provided by Intel CPU long time ago in a different operating system. I mean, in another my toy operating system. But it was very simple. But it looks like it is not used in the production.
You can actually enable it on Linux in the config settings. So if you trust the Intel generator, you can turn it on. And there's also another one for the bootloader provided randomness, which on ARM on device trees, it just goes in the device tree. So we actually turned that on in Asahi Linux because we are the bootloader. Actually, this is kind of interesting because we didn't know the Apple bootloader provides I think 64 bytes of randomness on boot, and we ended up needing more for Linux. And the thing is, there is no random number generator hardware in the device tree, and we were and the CPU also doesn't support the the internal instruction, and so we were wondering how it works. And Sven figured out that the secure enclave, the security processor, that the TPM kind of thing, that has of course that can provide randomness. But what I didn't know is that even its boot ROM, without booting it, has a get random number function. So we without booting everything, without loading the whole OS, we could actually write some code to get random numbers from there. But it's like, why didn't you just give us random number generator that the main CPU can use? Why do I have to ask another CPU for random numbers? It's like, you could just have two generators, one for each CPU. What? But yes, Mini now actually gets random numbers from there and passes them to Linux. So, because Linux has this issue, right, where if you don't have enough randomness on boot, sometimes things hang.
Yes. Randomness. Yeah, that's why they gave up merging startup random and startup random, right?
Yeah.
I saw that article.
Yeah. So Asahi doesn't have that problem anymore, because we actually get enough boot randomness to seed it. So.
Random number is
difficult.
difficult.
Right? Yeah. So many things can go wrong, right?
Yes, and implementing those things correctly is very difficult. And
I didn't know that generating a random number is so hard work for computers.
Because they're not supposed to be random, not because computers are supposed to be deterministic.
Yes. And the problem is that randomness has some levels, and you can easily achieve the pseudo randomness. But if you need a true or cryptographically safe randomness, then it will be difficult.
Yeah, and also people had some very weird ideas of how you're supposed to do random numbers in the past, like that you need to count how much randomness you have on the input and on the output and all that.
Yes.
And these days, we've figured out that that's silly. And like, as long as you have a strong seed, it's fine. You don't need to start counting bits on the way. But yeah, so Linux changed that super recently, right?
So yeah,
Interesting.
implementing operating system can reveal the dark part of the computer.
Yes.
But it's fun.
Yeah.
But it's fun.
Here's a
Yeah, that
question.
is the fun part.
Here's a question for you. Well, hold on. Does liumOS support SMP in any way, or is it always single CPU?
Good question. It does not support SMP right now, but it raised the what is that? The proximity info. You know, the NUMA nodes has the proximity info for getting the what topology of the memories. Because when I tested my operating system on the NVIDIA capable machine, it has multiple NUMA nodes, and we need to distinguish the local memory and the remote memory to do the right performance measurement. That's why I implemented those proximity info is stored in the ACPI table. So I implemented the parsing the ACPI table, SLIT or something like that. And I can show you how it works. But wait, QEMU does not have the SLIT, so I cannot. But good news is that I think I have some logs in GitHub, so I can show you how it works. So here is which one? Maybe this one. So this is the
So is this running on bare metal, not on the VM?
Yes, this runs on bare metal and on using the DLC80, the HP server machine with non-Intel NVDIMM, which is the battery. NVDIMM has multiple types of like so. Intel one does not use supercapacitor or batteries, but this one, the HP ones, HP NVDIMM is uses the. I guess they uses the supercapacitor to write back the DRAM content in the memory. And anyway, so we can see the show UEFI shows the here show SLIT shows the localities, and so this matrix means that there are two nodes, and the distance between two nodes are represented with the values, and that's it. So we don't have SMP support.
Yeah, because then you get into the really fun ones with memory ordering issues and synchronization.
Does Asahi Linux support that?
Yeah. We can do like on the Mac Studio, you get all 20 cores, so that all works fine.
Because basically no additional code is needed, I guess. Right?
Kind of like the bootloader actually has to initialize all the other CPUs, but once you provide them to Linux, it actually is using right now it's using what is called the spin table, which means that Linux the bootloader leaves the cores running on a loop, just waiting for events, and Linux just writes the entry point of where it wants the core to go on boot. So, and we provide that address to that entry point on the device tree. So basically, there's no code needed on the Linux side because the bootloader already starts all the cores and Linux just takes over them.
I see.
But the problem with that is that you can't turn off cores and you can't put them to sleep. So we're actually going to implement that, and we have a problem because the way that's done in a standard way on ARM is that there's a thing called PSCI, which is kind of it's a little bit like, I guess, ACPI calls, but it's not it's not
PSCI?
Yeah, it's basically there's two ways to do it. It's either a hypercall into the hypervisor, or it's a supervisor call into the supervisor. The problem
I see.
is the M1 does not support supervisors. And we can't make it a hypervisor because then Linux couldn't be a hypervisor. So we can't actually implement standard PSCI. And the idea right now, the plan is to define a new version of PSCI that uses UEFI functions on top of UEFI. And so then we can have a handler in UEFI for PSCI calls and like route it through there. But it's weird, right? Because like no other ARM system needs this. There's been several things that we had to change on Linux to support the M1 because no other ARM system anywhere uses them.
Wow.
like there are commits on the Linux like interrupt vector table assembly file for M1 support because we had to change things there.
Wow. So yeah, it's a bit different than normal ARM.
Yeah. Like the CPU is the same, but the system design is very different, right?
Yes.
Oh yeah. Cardologist Joey has mentioned on the chat that he already has a basic implementation working. So it actually already works. We just need to work on like sleep support and all the actual, the fun power management stuff. But the call API is already working.
That's cool. I should read the code. Actually, I tried to make an operating system on Raspberry Pi, which has ARM core. So yeah, I know the basics of I learned the basics of the ARM, but I haven't ported my operating system on it yet. So
do you plan to make Wasabi kind of portable or like abstract out the Intel stuff? It's hard, right? For now, I want to keep Wasabi as simple as possible and focusing on x86. So for some time, for maybe years, and I will keep keep Wasabi only supports x86. But after the implementation is stabilized, I will definitely try to implement port it into ARM onto ARM.
Cool. What is the
Because
next
it's fun.
step? Oh, sorry.
Oh, please go ahead.
What is the next step in Wasabi OS, and what is the missing component to support run execute my application in Wasabi OS?
So first thing is that we need to implement the merge tasking.
Oh, right.
And it is a bit complicated to write multitask things in Rust because Rust already has their threading or I mean the async and await mechanism, and maybe we can utilize it, but it can add another complexity here. So I'm still thinking about how to implement it, but I will. The main goal is that I port Asami's browser on Wasabi OS because we will going to I think it's a good idea to move to Wasabi OS as soon as possible because I don't want to maintain remote in C++.
Yeah, we need to write whole project in Rust. So like OS from scratch in Rust and writing application in Rust.
That's what goal. I wanted. That's what we want to do. So
yes, right. That's our goal.
That's really cool.
So that's what we are doing.
Yeah, that was a long story, and thank you for explaining lots of your OS things.
Yeah, thanks for hearing, everyone. Yeah, it's unbelievable that 42 people are still watching.
I like that number. I like the number 42.
Yes, 42.
Not particularly.
The answer to life, the universe, and everything.
Yes. So I think this is the answer of everything, right?
Write your own OS.
Yay! Yeah, we are writing the universe. We are writing the universe.
And then we can virtualize the world inside our own OS.
Yes, and
Yeah, let's-
making another world in the virtualized world, and so on and so on.
Yep.
I think this
turtles all
world
the
is
way down.
virtualized.
The problem is the M1 doesn't support nested virtualization. But the M2 will.
But we can implement emulation
That's true. We can
without
emulate
hardware.
it. Yeah, we can emulate it.
Without hardware support, but the performance will be a nightmare.
Yes.
But it is not a huge problem because we can virtualize any devices, including timers. So we can delay the timers to not to allow guests to notice that they are working very slowly.
You can just warp time like that.
Yes.
I actually had a problem with that, like in the
You
mini
mentioned in the last stream, right?
Yeah, but not just the time warp, like the mini hypervisor. Basically, you actually can't virtualize the physical, like the real timers on M1 properly. Like you need, like ARM, like Apple intended for that to be done using the virtual GIC, which is a standard ARM thing. But if you try to do it the same way the M1 does it, you actually can't, because it's a bit weird, but like there's no way of trapping accesses to the timer registers. And there's no way of like knowing when the guest acknowledges the interrupt without that. So that's why the hypervisor right now has like 1,000 hertz timer pull. Basically, it updates the interrupt state 1,000 times per second just to make sure that it never breaks. And there's no way around that. Like it's actually impossible to do properly. The only way to do it is with a newer ARM architecture version that has that feature, or using the GIC, which means the guest sees a different kind of interrupt controller. So there's
And which means it is impossible on Nemo Mac.
Yeah, it's literally impossible to correctly virtualize an M1 Mac on an M1 Mac with the real physical hardware.
Yeah, actually, virtualizing the time is a very difficult problem.
Yeah.
I found that Linux timekeeping is broken. Actually, I hit that problem in the work. So
Yeah, no, Linux. You probably seen the what was it, like? There's a message that Linux prints when the timer is broken, and it like falls back to another, like the TSC something.
Yes.
Yeah, that one. Yeah.
And also, timekeeping subsystem is designed when there is no virtualization. So that's another complexity for virtualized.
Yeah. Like ARM has that problem too. They don't have like the hypervisor can steal time from the timers, but then you don't know what clock time is, right?
Right.
There's like an ad hoc shared memory kind of interface that is defined.
Yes.
Pair of virtualized timers.
Yes.
This is so ugly.
Yeah, everything is duct taped.
Yes.
So yeah, if I implement, that's another reason why I write operating system by myself, because I can do better.
Yes.
I believe.
Look at it.
I don't want to maintain Linux kernel. It's broken.
Yes.
Yeah. So my hidden dream is that one day I will replace the existing operating systems with my operating system.
Look at it.
Yeah, great goal. Yeah, your operating system will be de facto standard in like 10 years.
Hope
10
so.
years. I hope so too.
Yes, we should do that, and then everyone can use NVDIMMs.
Yes.
Ah. Oh wait, Cardano just says Linux doesn't support nested virtualization yet on ARM 64. I didn't know that. I didn't know that.
Really? Really? I didn't know that. Neither.
Yeah, come to think of it, when I was looking at that code, I didn't see anything about that, so that makes sense. It's not there.
Makes sense. Makes sense. Oh. Wow. So yeah, I think many people think that operating system is finished thing. There's no room of improvement, but actually there are a lot of room for improvement. So please join us and make operating system.
It's really not that hard to start, like, a ToyOS like this, or even like, mini, like a bare metal boot code. Like, people think it's, like totally crazy, but you can actually build it from small pieces. So
yes, it's far easier than you thought, and thanks to UEFI, yes, it makes the world so much better. We don't need to do random things to switch the CPU from 16-bit mode to 64-bit mode, right?
yeah.
Thank you, UEFI. But interacting with UEFI is a bit annoying, though.
Yeah.
But there are UEFI RS crate already, so if you are okay to use existing crate, then you can use them. But I'm not using that. I wrote UEFI interfaces by myself.
Yeah, on the M1, the Apple doesn't use UEFI, so they have their own boot protocol, but it's pretty simple. It's just like loads your raw binary and jumps to it, basically. Actually, no.
Simple.
You know what's really funny? They used to use Mako, the like macOS binary format.
As a boot?
Yeah, for the kernel. Yeah. And I mean, UEFI uses PE, which is like worse.
Yes.
Yeah, but
that's because UEFI is designed by Microsoft and other folks.
So Apple uses Mako, but you know what's really funny is that we were using it, and then in version 12.1, I think it was, they changed the way it's handled, and our Mako binaries were no longer compatible with their tools. But at the same time, a raw binary option appeared in QEMU too. And it's just like, Apple doesn't use this. And I just know that some engineer at Apple added that for Asahi Linux. Because it's the only reason it exists. There's no reason for Apple to ever use that. You can't even set the right parameters for like the macOS kernel to boot because it's missing some special stuff. So it's literally for non-macOS systems.
Wow.
Some engineer at Apple did that. Thank you.
Yes.
Your project moves. Your project changed the world in Apple.
Maybe, yeah. Maybe
yeah.
they changed your project changed their mind. Oh,
right.
using Mako was a bad idea. Let's implement a low binary option. Or maybe the Apple folks did some hackathon to develop a new operating system on Mac, and they noticed that writing Mako is not a good idea. So
yeah. Actually, you don't want to see how we make the Mako binary because we still make it for like right now the hypervisor only notes Mako because I'm too lazy to change it. But the we built Mako files with an elf toolchain.
I know, yeah.
With a linker script.
Yes. And object copy or something like that, I guess.
Yeah. Oh, binary. It's like an elf that contains a Mako inside.
Do you know? It is possible that we can make a binary that can boot on Windows, Linux, and macOS with the same binary.
I
I
know
don't know
Windows
that.
because of the B header offset, right? But
Yes,
how
yes,
does it
yes.
work with Mako and elf? Don't those both need a magic in the beginning?
I forgot the detail, but they found a way. One person found a way to do that.
That sounds horrible.
Yeah. Windows.
Like P elf, yeah. Like polyglot or something. Oh, actually, or that one, yeah. Oh,
Yes.
What?
Yes, I think this for everything.
Oh no, but that's just a shell script, right?
Yes. Right. So I was wrong. So it can be executed on all of the three major operating systems, but they're not making the compatible binaries for
Right.
all of the formats. Yeah, that is impossible. I think.
Mako and elf is probably impossible.
Yeah, completely different there. Yeah. So that's it.
Thank you so much.
Yeah, it was fun. So much fun. Yeah.
Yeah, it was really fun. I learned a lot of things from your talk. Actually, I didn't know that lot of things.
Yeah. Yeah, please, teach us more about M1 Mark and.
Oh yeah, definitely, yeah. We should do this more. Like, there's so much stuff to talk about. Like last time it was about the reverse engineering, but like there's so much more with the how the bootloader works, how the hypervisor works, and all the other hardware.
Yes.
Yeah.
Also, we want to make a notebook computer with NVIDIA, right?
Oh yeah. We need to
Right.
investigate that. I'm gonna do that. That sounds like an amazing project.
Yes.
Yeah, I also
need
want
to
to
do
contribute to Asahi Linux in the
Oh
future.
yeah, definitely.
That's
That'd be
one
awesome.
idea.
Yeah, no, definitely. Like, it's you can just work on whatever you want, just whatever you're interested in, or the bootloader, the drivers, anything, like, just whatever you want to do, feel free.
Yeah, thank you.
Thank you so much.
Yeah, I will find what I can do, but I think there are many things, right?
Oh yeah. Like, there's always because there's so much hardware to support, right? So like the video encoders, the decoders, the neural engine, and also even things like temperature sensors and
temperature sensors.
Yeah. Like there's a lot of random things. So yeah, no, definitely, that'd be great.
Yeah, that sounds nice. Yeah, I look forward to collaborate more in the future.
Yeah. And I want to try like liumOS and Wasabi and see how it works, cause like,
Please don't do
Yeah, we will show our progress
Yeah.
again.
Yeah. I think you can build. Actually, it's I set up CI for liumOS, so it can be built, but I can't assure that it can be booted on the real hardware. So please be careful. But you're the operating system developer, so you know the risk.
It's fine. That's great.
Yeah, thank you. Thanks for inviting us.
Yeah, absolutely. It was so much fun having you.
Yeah, thank you
Great
so
to be
much.
able to talk about this stuff.
Yes.
Thank you so much.
Yeah, thank you too.
So, does anyone have any questions or anything you want to say? Did you like it? What do you think about
Yeah.
DIY OSs? Are you gonna try working on that?
Anything, any comments are welcome, and please feel free to send us a reply through Twitter or anything, and and also please make sure to check our channel as well.
Yeah, sure. Please.
Yeah, unfortunately, it is most of the videos are in Japanese. But if you maybe it's a good opportunity to learn Japanese.
I mean, that's always a good thing.
Yes.
But if you have any questions, like you can ask anything in English, but we can,
Yes, we can understand English. So
the reply
Actually,
to the question in English.
Luna
Right.
asked if you're interested in Inochi 2D, like in 2D VTubing. As well as 3D VTubing. Just wondering if you're interested in that.
I mainly use 3D VTubing. So, but how do you think? What do you think, Asami-san?
Oh, I mean, we gonna use Inochi 2D models.
Like,
Oh,
are you interested
that
in
sounds
that
nice.
kind of thing?
Yeah, I'm interested in. But I don't have a talent to draw 2D
Yeah,
anime characters.
Same here.
I mean, I didn't draw my model. I asked a friend.
We need the illustrator.
Yes.
Yeah.
And I think 3D model, moving the 3D model is easier than
Yeah.
2D
Like,
model.
it's really hard to do like hands-on 3D models. So
Yes.
actually, someday I want to get a 3D model too, like not to replace the 2D model, but to use both, right? So like I can do like VR games and that kind of thing. That would be really cool. Yeah.
Oh, do you know Vload Studio is there?
Yeah.
But so you can try Vload Studio to make your own avatar, but it can be difficult.
I can try. And yeah, like I think there's people working on collaboration tools that will work like across different platforms, like 2D and 3D stuff. So instead of using like video like calls, you can just send the motion data and render it locally, and it'll be like really nice and high quality. So
More interesting.
Yeah. There's people working on that,
I'm really interested into it, and also some friend VTubers are also interested in making such kind of not operating system. Sorry.
VTuber OS.
Maybe, eventually we can port that application to my operating system, but not for now. Anyway, I'm really interested in that project. So please,
sounds cool.
Invite us.
Yeah. All right. So I guess that should be a wrap for today. It's been how long? Oh, it's been 3 hours.
Wow, it's quick.
Time flies, right? When you're talking about this stuff.
Yes.
Right.
So thanks for coming and watching our stream.
Thank you, everyone.
Thank you for having us.
All right. Thank you so much. Bye-bye.
Bye bye.
Bye bye.